Hey everyone, welcome to this next video of Quantum Computing Podcast. And in the last video, we had just finished this exercise on page number 11. And let's start it from there in this video. All right. So this is where we were. We had just finished this exercise of calculating the product of two complex numbers. So let's start from there. What comes next? All right, so these are the two properties of these two operations, addition and multiplication. So these equations 1.16, 17, 18 and 19 tells you that these operations are commutative and they are also associative. So you have I'm sure you have encountered this two properties in this elementary algebra or maybe somewhere else. And what it says is that if you want to add two complex numbers in this case, then you can do this addition in any order. So if you want to add C1 and C2, you can add C2 to C1 or C1 to C2, or C1 plus C2 equals C2 plus C1. And this is very intuitive because if you look at the definition or the way we were doing this addition for the complex numbers was that we were doing it component wise. So complex number, remember, is an ordered list of two real numbers, at least in this new notation that we saw in the last video. And the addition was nothing but the component wise addition. Okay, and even if we don't use this notation, the addition that we had defined was literally just the component wise. So if it's the component wise, then it just makes sense that the addition of complex numbers can be done in any order. For the multiplication, it's not that intuitive, but let me infuse that intuition. So if you look at again, going with the same notation that complex number is nothing but an ordered list of two real numbers, we defined multiplication with this formula. And if you look at the result of this formula or the formula itself, it is the combination of component multiplication, and that multiplication is being added or subtracted based on which order it is in the list. So here it's still the component, it's not the component wise multiplication, but it's still the multiplication of these components, right? So and you can prove it as well. You can take C1 as A1 B1 and C2 as A2 B2, and C1 into C2 is this. Try to calculate C2 into C1, you would arrive at the same result, right? And so here the intuition is that it's not the component wise multiplication, but it is still the multiplication at the component level in a certain way. So you can prove it very easily that this is also commutative. Basically, if you want to multiply C1 and C2, you can do it in any order. And as they are commutative, it's very easy to prove that they are associative as well. So if you want to add three complex numbers, you can add any two of those three complex numbers first, and you can add the third complex number to the result. And you can do it in any order, and it's not going to matter. And it goes back to the being commutative, right? So if you add any two numbers, then you can do that in any order because the addition is commutative, and the result is just another complex number, right? The addition of two complex numbers is just another complex number. So now that complex number can also be added to another complex number in any order because addition is commutative. And you can also prove it with some arbitrary examples like C1 is A1 B1, C2 is A2 B2, C3 is A3 B3, and you can arrive. And that's exactly what actually we are going to do in this operation, proving this property that multiplication is associative. So let's do it with example. We can either do like this: C1 is A1 B1, C2 is A2 B2, and C3 is you know what, I think this might get confusing because then it will just give us a large term, might be hard to follow. So we can pick like just any arbitrary numbers, right? Let's say C1 is what are the good numbers? Let's say -3, -1. I'm gonna pick 1 somewhere so that the multiplication is easy. 1 minus 2, C3. You know what, let's make an exception. 3 minus 2. Okay. So if you wanna say, see, I'm picking the small numbers, so it's easier to do multiplication in head. So let's say C1 into C2. Okay, so A1 into A2 minus 3 into 1, which is -3, minus B1 into B2 minus 2. Then A1 into B2, which is -3 into -6, which is 6, plus -1. Okay, so it gives you -5 and 5. All right, so this is there. Now if you do C1 into C2 into C3, okay, so basically you're multiplying -5, 5 into 3 minus 2. So this would be -5 into 3, which would be -15 minus 10. So -10, right? And that would be, yeah. So -5 into -2 would be 10, plus A2 into B1, which is 5 into 3, 15. So this is -5 plus 10, it would be -5, 25. All right. Now if we do C2 into C3, it's -2 minus -2. Oops, sorry, my bad. So C2 would be 1 into 3 minus 4. And then 1 into -2 would be -2, plus 3 into -2 would be -6. So 3 minus 4 minus 1, -8. And then if you do C1 into C2 into C3, yeah, let's just do it straightforward. So that would be, how would it come? Let's say 3 minus 1 into -1 into -3 minus 1. Oh, we are doing C1 now. 3, and then it's gonna be -8, right? Yep. And then minus, so it would be 24 plus 1. That would be, yep, so same result, -1, -5, 25. Okay, so that's your exercise. All right, so then the next formula says that that multiplication also distributes over addition. Okay, so if we have C1, C2, C3, C1 multiplied by C2 plus C3 is the exactly same if you multiplied C1 into C2 and added that with C1 multiplied by C3. Okay, and the next the paragraph, this line of actually equation just proves that it's true. Okay, actually all the way up to here. So read through it, or maybe do it and then compare it with the steps given here. All right, now it says that let's go into subtraction and division. And see, this is a new set of complex numbers, so we can actually define any operations the way we like. Okay, but if we are using the words like multiplications and division, then we would like them to be complementary to the what you can say, addition and subtraction. Addition and multiplication. Okay, so if you want to define subtraction, because we are actually defining, then we can define subtraction as the complementary operation to the addition, and we can just say, you know what, subtraction can just be defined as component wise. Okay, very, very simple way. And this gives you C1 minus C2 as A1 minus A2, B1 minus B2. Straightforward. And for division, let's say, and again, see, this is the defining part, right? We can define the way we like, but if you want to define division as the complementary operation to multiplication, then we have to define like this, right? That if x and y is the ordered list of a complex number, which is the result of division of C1 and C2, then this is what is xy is a1 b1 a2 b2 over a2 b2, and that also means that a1 and b1, if you just move a2 b2 there, is the result of xy multiplied by a2 b2, which is this. All right, so a1 is nothing but the first term and b1 is nothing but the second term. All right, and that's exactly what it says here. And this actually this page also gives you how can you even solve for x and y. So if you want to solve this two equation 1 and 2 for x, then you just have to multiply the first side with, first equation with a2 and the second equation with b2. You get these results. The reason I'm not writing it on the index card and not going through this is because it's already given. It's right there. Okay, either you can read through it, and reading, if reading is not your way of consuming this kind of information, then maybe do it on site. Okay, use this blank page, do it on a notepad or something, and then come back and compare your steps with this. And that's exactly what I did actually when I was going through this on my own. Sorry, I actually did this, right? I compared, I did it on a notepad and just compared it with the steps. So you can always do that. So finish that, finish reading that, and maybe go all the way up to the end of this paragraph just after equation 1.36. And in the next video, we're gonna pick up example 1.2.2. We'll start it from here on page number 12. All right, okay, thank you.